Ideal gas law.
It's not testing.
Okay. Ideal gas law. The ideal gas law tells us things about gases, as opposed to the less than ideal gas law or the suboptimal gas law. Ideal gas law is, when we write it simply, is PV equals nRT. And why the N is not capitalized, I don't know. But that's just the way that it is. Nerd. Yep, that's what it is. Yes, Vince. I have started recording. I have a, thanks for making sure, buddy. Hey, you failed to do that earlier. Can you try it again? All right. Yeah, we got the red dot. We're good. Okay, PV equals nRT. Okay? Anyone want to take a guess as to what P would stand for?
Power.
Power. No, it's pressure. Anyone want to take a guess as to what V is? No. There you go. Everybody was so confident. It's velocity. No. Also, when or slash if you take physics, physics treats gases like they don't even exist. Physics is like, whenever you're calculating anything in physics, it's always ignore air resistance. And it's like, listen, we don't ignore air resistance here because we care about the gases. Okay? We care about the noble gases and we care about the peasant gases. Okay? So PV equals nRT. N, lowercase n, again, no one knows why, is the number of moles. Moles. It's the number of molecules in measured by moles. No. Because no, if you're mad about the N, wait until we get to the R.
No.
R, it is not the ratio, it is the gas constant. I told you that you were going to be mad about it. Okay? The gas constant, and there are many constants in scientific laws. So remember that in science, when we talk about a law, what that means is it's math. Okay? It's related to math, and it can be proven mathematically. You can write a mathematical proof for it. Okay? Remember that a law is just a part of a theory, right? So the ideal gas law is a part of chemical and physical theory. Okay? The gas constant changes depending on what unit you're using. So it's not very constant. But I know, I was typing on my on my screen. And I can never remember what it is because there's multiple different values for it. It is, what is it? Let's see. Oh gosh, so frustrating this. Okay, so we use atmospheres, kelvins, and moles. Moles. And so don't get mad at me, okay? Don't get mad at me. Just be nice, okay? So if we use atmospheres, moles, centimeters cubed. Yeah, wait. Yeah, 82.057. Yeah. And I'm gonna write the unit down. Don't freak out. Just don't freak out. It's centimeters cubed. Centimeters cubed. Let's see here. Atmospheres. Kelvin to the -1.
You should have stopped at 7.
Moles to the -1.
Why is there an ATM in the equation?
So that's atmospheres. So don't worry too much about the unit. You don't need to like freak out about it, okay? Again, when we use constants in mathematical and scientific laws, they have really stupid units. Woo! Okay? But really what you need to understand is that it's 82 if we're using these units, which we will always use. Centimeters cubed, atmospheres, kelvins, moles. Okay? We can measure the pressure in pascals or millimeters of mercury or inches of mercury or, anyway, it's stupid. Anyway. Okay, anyone want to take a guess as to what the temperature is? Dang it, what the T means. Fetch. I already gave you the answer. Yeah, it's temperature. Okay. And this is in kelvins. In kelvins? Kelvin? Yeah. It is a measurement of temperature, and it's not in degrees Kelvin. A lot of people like to say degrees Kelvin. It's not degrees Kelvin, it's just kelvins. Celsius? His name was Lord Kelvin. Yeah, he was a British lord.
A British lord?
Yeah, he was so in Britain, you know, here we have the House of Representatives and then we have the Senate. In Britain, they have the House of Commons and the House of Lords, which is essentially like the fancy schmancy old white guys, and then the people that are just like, anyway. So Lord Kelvin, he was a member of the House of Lords. Volume, we use centimeters cubed, or cubic centimeters.
There's a difference?
Oh no, it's the same. You just say it different. Cubic, centimeters, centimeters, just to make you all really mad, I'm going to do it the British way. Centimeters. No, that's the way the British do it. And pressures we do in atmospheres.
But is that the same thing as centimeters? Like centimeter with a little 3?
Yes. Centimeters to the 3rd power. Okay? All right, that took long enough. So when we do the ideal gas law, so we're gonna do our for instance our balloon. Okay? Our balloon full of hydrogen that we did the splody. We did the splody. Okay?
No.
Our balloon was green, huh? So we're gonna make a very inappropriate assumption that the balloon that we sploded was spherical.
Why would it be spherical?
It definitely wasn't, but we're just gonna, for mathematical reasons, I don't want to calculate the volume of a balloon shape. Because it's a freaking, because it's a half sphere plus a cone, and it's, at what point do you double, anyway. Make it work. So we're just gonna do a sphere, and we're gonna say that this sphere has a diameter, thank you, of 20 centimeters. Okay. The internal pressure of, what's the word again? Balloons is is the internal pressure of balloons is, wait, let me write the equation again, nRT. Internal pressure of balloons is 1.05 atmospheres. Okay, so an atmosphere is a measurement of pressure, and 1 atmosphere is equal to average atmospheric pressure at sea level on Earth. Sure. So one atmosphere is atmospheric pressure at sea level on Earth. Okay? So inside of a balloon, it's 1.05, just slightly higher. Okay? The temperature, sea levels are barely, well, yes, they are rising, but anyway, we'll talk, that's a different subject. Okay, so, so we have the pressure, oh, the temperature in here is 290 kelvins. Okay. So remember that a Kelvin, is the same scale as Celsius, but it doesn't have negative numbers. The starting point of Kelvin is 0, which is absolute 0. So 0 degrees Celsius is equal to 272-ish kelvins. So room temperature is about 290 kelvins. Well, kelvins and Celsius are what we use in science. If you're using physics and some chemistry, you use kelvins. Most other things we use Celsius, but
one universal temperature.
well, we just need to we need to kill Fahrenheit with fire.
Can we kill Kelvin?
No, Kelvin, we need kelvins. Because kelvins is a measurement of absolute temperature. Okay, we need kelvins. And we need Celsius because we need it for biology reasons. Because Celsius, you need Celsius so that you can have a 0 where water freezes. Okay, anyway, 290 kelvins. The pressure, now we need the number of molecules in moles, which is 0.2 moles, right? Because that's how many moles we had in the balloon. Keep on forgetting that word. Balloon. 99 red balloons floating in the summer sky. Okay, good. Because for a second there, I didn't know if anyone recognized it, and I was going to feel extremely old. All right, 0.2 moles. So we have pressure, we have volume, we have number. Oh wait, we don't have volume yet. Volume. So the volume of a sphere is 4/3 pi r squared, pi r cubed. Sphere equation. Volume. I'm pretty sure, yeah, 4/3 pi r cubed, okay? So if we use the r, which is half of the diameter, so it's 10. 10 cubed is 1,000 times pi would be 3,140. And then 4/3 times that's going to be like 4,400. Okay, so we had like 4,400. Oh, yes, I just did that math off the top of my head, and it's probably wrong. 4,400 cubic centimeters. Yeah. Okay. Which is equal to 4 liters, 4.4 liters. Okay, so we have all that stuff. Temperature. Oh, and then the what is it? 800 and what's the R? 820? No, 82. 82 is R. Okay. So with these numbers, we can figure out some different things. All right. So for instance, maybe we measured the size of our balloon, and it was that size, but we think we had 0.2 moles. We think, but we don't know for sure. You know what I'm saying? We want to know exactly how many moles we created. So what we can do is we can use these numbers to calculate exactly how many moles we actually had in the balloon using these numbers. The way we do that, we just solve for n. And the way that we do that, so you've taken algebra, yes? The way that we can solve for n is we simply move the RT to the other side of the equation, right? So n equals PV divided by RT. Yeah? No?
No, I don't like that.
Why not? This is algebra. This is just algebra, people. You just move things around, right? Okay, so n equals PV over RT. So if we do 1.5, or sorry, 1.05, which is our pressure, 1.05, and we multiply that by our volume, which is 4,400. Again, the number is probably wrong because I did it off the top of my head. I should probably actually calculate it, but whatever. 4,400 cubic centimeters, and we divide that number by RT, which R is 82.057. 82.057 multiplied by the temperature, which is 290. Wait a second. No. 4,620. Yeah, wait. Sorry, I got to redo this because the orders of operations was wrong. 5,7 multiplied by 290, 290. And then we do 4,620 divided by that number. Right. What? Sure, dude. Crap, where's the ant? There it is. So by using all these numbers, we can calculate this. So let's write this all out. Okay. So to reiterate, if we want to solve for n, all we have to do is n equals PV divided by RT. And let's just copy and paste our numbers here. Well, copy. Mm-hmm. Paste. Okay. So what we can do is we take 1.05 multiplied by volume, which is 4,400. And we divide that by, we need to put this in parentheses, 82 multiplied by what's the other? RT, 290. 290. So if we do that math, so we know that we think that we made 0.2 moles of hydrogen. What we're doing is we're calculating, given our observation, how many moles of hydrogen we actually made. And the answer, when we do that math, gives us 0.194. Is 0.194 pretty dang close to 0.2? It's extremely close, right? So we have validated that we made 2 moles of hydrogen in that reaction. Okay? I'm going to stop the video here, and we're going to do some practice problems. Don't worry, people at home, we'll do some more practice problems on this probably next time. Okay? Questions on any of this? Huh? Like and subscribe, yeah.